Hello everybody, this is Dr. Christopher White and welcome back for part 2 of our video dealing with the lab exercise Interpreting Geologic Maps. So in previous lab exercises we have discussed that when looking at geologic maps, especially those for areas that have been tectonically deformed, it's not uncommon for you to see repeating strata. So you'll see the same layers of rock occurring in your geologic map several times. Now, there are two main causes for this repeating stratigraphy. The first one is faulting and the second one is folding. So in the case of faulting, we are going to start by looking at this diagram over on the right hand side again. So we're going to primarily focus on thrust faulting. So obviously we have the map view at the top and the cross-section view at the bottom. So in the cross-section view, you will see that the up-thrown block, the overriding block of rock, is marked out in green, and that's being pushed over this orange block below. Now, if you imagine that this green block consists of two separate layers of rock, these two separate layers are going to be pushed over the top of this orange block. Now, typically in areas that have undergone thrust faulting, you don't just get one thrust fault. You will often have several thrust faults and they will be stacked one on top of another. And that means each thrust fault will be pushing a layer of rock over the top of the previous thrust fault. So this will lead to the development of something which is sometimes referred to as a thrust duplex. Now, if you imagine that each one of these sheets of thrusted rock that's being pushed up contains layers of rock A and B, well, the thrusting is obviously going to result in layers A and B being pushed to the surface for each thrust fault. So you're going to see the same layers of rock being repeated again and again and again. Now, in terms of discerning when that is happening on geologic maps, it's relatively straightforward because the fault itself will be marked, or should I say the faults will be marked. And so you'll be able to tell pretty quickly that there is a fault there and what type of fault you are dealing with. And very often when you do see repeating stratigraphy, the most common cause of that will be thrust faulting. So you will see the distinctive sawtooth pattern associated with the thrust faults on the geologic map. Now, the other method of producing repeating stratigraphy is folding. So if we look at the diagram over here, you can see we have a sequence of rocks that have been folded into anticlines and synclines. So obviously we have an anticline followed by a syncline, anticline, syncline, and the start of another anticline. And this is very, very common. So typically when you deform an area, you don't just deform one block. You will be deforming the entire area. So you don't just end up with one anticline or one syncline. You will typically get multiple anticlines and synclines, often of different sizes within your map area. So you might end up with 2 or 3 very, very large anticlines and synclines, and along the sides of those large anticlines and synclines, you might have smaller anticlines and synclines. So it can lead to some very, very complex folding. Now, if you look at the diagram here, if you look at the map view on the top, you can see that we have the same layers of rock being repeated due to this folding. So you can see we have this darker blue layer, this lighter blue layer, the yellow layer, and the grey layer, and they are repeatedly occurring at surface. Now, if you look at these anticlines and synclines, you will see that there is a red line, which is running along what we refer to as the axis of the anticline and syncline. This region is also sometimes referred to as the hinge. And this is the point in the middle of the anticline and syncline that essentially marks the position where the rocks are actually being folded to produce the anticline and syncline. So this is the middle of the anticline or syncline. And these will be marked on geologic maps, typically with a red line. And the red line will often have arrows associated with it. And you will see that for anticlines, these arrows are pointing away from the red line. In the case of the syncline, the arrows are pointing towards the red line. And this is a reflection of the dip associated with each of these structures. So in the case of an anticline, what you have is you have one limb over here that's dipping off in this direction, and you have another limb that's dipping off in this direction. So the arrows are essentially pointing away from the hinge and telling you the rocks are dipping this way, and this way away from the hinge region. Therefore, you have an anticline. In the case of the syncline here, you have layers of rock that are dipping towards the center of the syncline. So you have one limb that's dipping down like so, and another limb that's dipping down like so. And so the arrows are essentially telling you the layers of rock are dipping towards the center of the structure, and as such, you are dealing with a syncline. You should also remember from physical geology that when you're looking at anticlines and synclines, you can also distinguish them on maps based on the ages of the rocks that make up the anticline and syncline. So in the case of anticlines, in the core of your anticline, you will have the oldest rock. And you can work that out because associated with your map, there will be a stratigraphic column. So in the case of the anticline here, you can see in the core of our anticline, we have the oldest rock. And as we move towards the edges of our anticline, the sides of our anticline, the age of the rocks is getting younger. So we're going from the oldest orange layer here all the way through to the darker blue layer here. In the case of synclines, it's the reverse. You're going to have the youngest rocks situated in the center of your syncline, and the rocks are steadily going to get older as you move away from the core of your syncline. So these are going to be the youngest rocks in the middle of your syncline, and as you move away from it, the rocks are going to get progressively older. So when looking at geologic maps, you can identify anticlines and synclines by the repeating stratigraphy, the fact that there will be a map symbol there telling you it's an anticline and syncline. And even if there isn't a map symbol telling you that it's an anticline or syncline, you can actually just look at the stratigraphy and use the ages of the rock layers to gauge what kind of feature you're looking at. Is it an anticline? Is it a syncline? So there will be plenty of data on your geologic map to help you analyze it and work out what kind of features are producing the repeating stratigraphy when you see it. And so you should hopefully be able to work out relatively quickly, based on the map symbols primarily, are you looking at an area that's been faulted, or are you looking at an area that has been folded? I should point out, in most cases, you see these features, these anticlines, synclines, and faults, associated with areas that have been tectonically deformed. So it's not actually uncommon to see both geologic structures in the same map area. And so you will have to analyze what you're seeing and try and work out, right, is this repeating stratigraphy due to the big anticline I see here, or is it a result of crust faulting? Now, if we continue down, we can see some top-down map view diagrams for anticlines and synclines. So this is what you would see when actually looking at your geologic map. So in the case of an anticline, you can see we have these two dip symbols either side of the axis of our anticline. And you can see that based on the dip directions for the layers of rock, they are clearly dipping away from the hinge. The hinge in this case is marked out in black, but most geologic maps, or well, at least most modern geologic maps, will have it marked out in red. You will also notice that the arrows are pointing away from the axis of the anticline. This is also telling you that the layers of rock are dipping away from the hinge region, and obviously that also tells you that you are looking at an anticline. In the case of the syncline, in this instance, you can see that the axis has been marked out in red now. You will notice that the dip and strike symbols for the layers of rock either side of the axis show that the layers are dipping towards the axis or towards the hinge. And so this is also shown by the arrows. You can see the arrows are now pointing towards this axial line, this axial trace. And so that also tells you you are looking at a syncline. And later on in one of the lab exercises, you are going to have to analyze a area of deformed rock, and you're going to have to place the correct symbols for that geologic structure. Is it an anticline? Is it a syncline? So you are going to have to return to this diagram later on in the lab exercise. Now, when we look at areas of folded rock, as I previously touched on, you tend to get multiple anticlines and synclines in the same area. And once again, you can see another diagram where we have a set of anticline, syncline, anticline, syncline. So when we look at them, it's not uncommon for you to see this very, very distinctive sawtooth sawtooth-like pattern. So this sawtooth-like pattern is a very, very common indicator for the presence of anticlines and synclines. And you can see it in a simplified map view in this diagram over here as well, labeled C. So what's actually going on in this diagram? Well, in this diagram, we have a situation where the anticline and syncline is not perfectly horizontal. And this is extremely common in areas of deformed rock. So in theory, if your anticline and syncline was perfectly horizontal, it could go on forever. But, we live in the real world. So there will actually be a slight dip to your anticline and syncline. And so this means eventually the layers of rock that form your anticline and syncline will eventually start to dip into the subsurface. And so if we look at this diagram here, you can see that these layers of rock, this darker green, this kind of pink, this kind of pink red, and this minty green color, you can see the layers of rock clearly have a dip. And they're dipping off towards this northeastern corner up here. Now, because of this dip, the anticlines and the synclines are going to be dipping down towards this top edge of our diagram. And this dip of the anticlines and synclines is referred to as their plunge, because they are plunging beneath the Earth's surface. So when we look at our map symbols for our anticlines and synclines, you can see we have repeating stratigraphy. So straight away, we know there's got to be anticlines and synclines or faults. We don't have any map symbols for faults, so we can assume with relatively good accuracy that what we're seeing is the result of folding. So we're looking at anticlines and synclines. And then we can use the ages of the rock to work out what type of feature we're looking at. So in the case of this feature, you can see we have this green layer of rock here, which is over here in the stratigraphic column, followed by this pink layer, which is here, followed by this pink-red layer here. So we can see as we move away from the hinge region, the rocks are getting younger. So we have oldest rocks in the middle, youngest rocks on the edge. This is going to be an anticline. In the case of this feature here, you can see that in the core of our feature, we have this mint green colored rock, which is this layer right here. Then as we move away from the axis, we can see we move into the red pink layer, which is this layer. Then we move into the pink layer, which is this layer. So we are moving from younger rocks, and as we move away from the core, away from the hinge of our syncline, we can see that the rocks are getting steadily older. So we have younger rocks in the middle and older rocks towards the side. This is telling us we are looking at a syncline rather than an anticline. Now, providing these synclines and anticlines were produced by the same deformation event, they will typically all be parallel to one another. So you can see in this diagram here, the orientation, so the strike of these features, so the strike of this anticline, this syncline, and this anticline are all approximately parallel to one another. This is a good indicator that they were formed by the same geologic event. Now, what this also means is because they were formed by the same geologic event, they're going to have similar features. And in this case, one of the similar features is going to be their plunge, the fact they're dipping into the earth at approximately the same angle. And so we can see, due to the plunge, we can see our anticline is closing up as we come towards the top of our diagram. We can see that the syncline is closing up as we come towards the bottom of our diagram. And then we can see this anticline is closing up as we move towards the top. And then we're moving into another syncline here, which is also closing up towards the bottom. And this produces a very, very distinctive zigzag kind of shape, also referred to as a sawtooth pattern. And so this is a very good indicator of multiple anticlines and synclines all plunging into the earth, producing this very, very distinctive pattern on your geologic map. Now, the plunge direction of your anticlines and synclines is marked out on the anticline and syncline map symbol. So you can see here's our anticline symbol, here's our syncline symbol, and you will see at the end of the line we have an arrow. And that's showing you the direction of plunge. So it's showing you, right, the axis of your anticline is orientated along this line, and it is plunging into the earth towards the top of our diagram in this case. And the same is going to go for the syncline as well. So even though the syncline is closing up towards the bottom of our diagram, the plunge of the feature is still going to be towards the top, because if we look at the dip here, we can see that these layers of rock are dipping off towards the top of our diagram over here on the right hand side. So for this anticline, this syncline, this anticline, the plunge is going to be the same. Now you will notice that there is no value given, so there's no angle for the plunge for each of these features. This is relatively common. So typically you will not see any kind of value next to the arrow. Very rarely you might, but most of the time the map symbol is simply telling you, right, this is the direction in which this package of rocks is plunging beneath the Earth's surface. Okay, so for part 1 of our lab exercise, we are going to begin by predicting the position at which a bed of rock will outcrop at the surface of the Earth. So this method is used to predict locations for planar, so flat layers of rock. So we need stratified rocks in order to use this particular method. And these stratified rocks cannot be deformed. So there can't be any faulting, there can't be any folding. It just has to be a nice flat layer of rock. Now this layer of rock can be tilted, so it can have dip, but once again, no faulting, no folding. If that's present in the area, that's going to make the use of this particular method nearly impossible. Now, this method was first pioneered by William Strata Smith, and it actually allowed him to predict areas where he would expect to see certain layers of rock outcropping at the surface of the Earth. Now, what was realized was that you can predict the location at which a bed of rock will outcrop, providing you know 4, or at least have access to 4 pieces of information. Number 1, the dip angle of the bed in question. Number 2, its dip direction. Number 3, you know a location where the bed of rock has already been examined, so it's already known to occur at a starting location, preferably an elevated location. And you also have to have access to an accurate topographic map. This is something that in the early 19th century was not particularly common, but they were beginning to make an appearance. So as you move through the 19th century and into the 20th century, this particular method becomes more and more efficient because you begin to get better and better topographic maps. And you need a topographic map which is accurate because you are going to be using the contour lines on the map to help you locate probable locations or probable trends for where this particular layer of rock will be outcropping. Okay, so once again, providing your layer of rock has not been faulted or folded, you can use this particular method. And so how's it going to work? So over here on the right, you can see we have a map, and it's a topographic map. There's no geologic information on it whatsoever. So there's no rock layers, there's no dip and strike information, nothing. Now, the red point over here marks the position at which a rock layer has been identified. So the particular layer has been examined at this outcrop, and dip and strike information has been collected. So we know the dip angle of the layer, we know the dip direction of the layer, and we know the strike of our layer. Now, once again, providing we have no evidence to suggest that this layer of rock has been folded or faulted, we can then use this information to predict where this layer of rock will outcrop. Now, in the case of this particular layer of rock, it was first observed at a height of 1,850 meters. And when it was measured, the layer of rock has a dip of 10 degrees. And that dip is to the west, so towards 270, so over to the left-hand side of our diagram. So we know that this point here is 1,850 meters above sea level. we know the layer of rock has a dip of 10 degrees and we know it's dipping towards the west. So what we can do is, with that information, we can align a piece of graph paper with the dip direction of our layer of rock. So in the case of this outcrop here, we know our layer of rock was dipping towards the west, and we know it's dipping at 10 degrees. We can also look at this map here, and we can get an idea of the contour line spacing. So that's the gap between the contour lines. And in this case, the contour line spacing is 50 meters between the major contours being the darker, thicker contour lines. So what we'll do on our graph paper is we will start with the elevation of our first locations. This is 1,850 meters above sea level. And then on the rest of the y-axis, we are going to go down in 50-meter increments. So 1,800, 1,750, 1,700, etc. Now, also on our graph, we are going to draw a point directly below our red point on the map, and we are going to draw it on the 1,850 meter line. We are then going to draw a line coming off this point at 10 degrees, because that's the dip of our bed, and its dip direction is going to be towards the left-hand side of our graph paper, because that is the dip direction of our layer of rock towards the left-hand western side of our map. So what you will then do is, for each of these major measurements, so 1,850, 1,800, 1,750, and 1,700, you will notice that I have then drawn lines coming vertically off these points onto the map above. Now, to be clear, if you were doing this in real life, you would draw these lines very, very faintly and then you would erase them afterwards. But in this instance, I'm keeping them on there to help you see what's going on. So every time that this line crosses a contour that has a height of 1,800 meters, I will make a mark on my map. So you can see it crosses the 1,800 meter contour right here. It crosses the 1,850 contour here and here. So even though it crosses the same contour twice, you have to mark both locations. You don't just mark it once, you mark it every time it happens. For 1,750 meters, you can see it crosses the contour here. And for 1,700 meters, it crosses the contour here. Okay, so what are we going to do with this information? Well, what we're going to do is we are going to use these points to actually predict approximately where our layer of rock is likely to outcrop on the surface of the Earth. And in order to do this, we are going to use the points that we've just drawn, and we're going to use the contour lines. Because remember, the topography is going to affect where this layer of rock is likely to outcrop. So if you look at this diagram, you will see that the likely points, or likely line, should I say, at which this layer of rock is going to possibly outcrop has been marked by this blue dash line. So you can see what I've tried to do is I've done my best to follow the contours between the points. So you can see you have a kind of a head point here, and then you're dipping off into this feature here, and then you're coming back up again, following the contour lines. And then for each of these valleys, you will see that the line is stepping in slightly to take account of the topography. So we are going to start at our red point, and we're going to start drawing our line following the topography approximately. Doesn't have to follow the contour lines. This is an approximate. This is an estimate. You're going to come round following topography. You're going to keep going. You're then going to follow the topography for the valley, and then you're going to follow here. Now, in this case, you will notice that things get a little bit complicated here, because clearly there is some kind of feature here. And we know our point is here, so we know the line's going to step out following this feature, following this edge of it, should I say, following this promontory. And then it's clearly going to come back down on the other side here. Now, once we get to this point, the situation does become a little bit more complicated. You have a couple of possible options. You could just continue your line across the contour lines like so until you make it down to this point here. Or if you wanted, you could instead draw your line following the contours, coming down like here, following the contours for as long as you can, and then maybe coming out like that. Both of those paths would be considered valid because they would have, both of them follow topography to some degree, and both of them manage to intersect with this point down here. And then you will notice that the line doesn't just begin at the red point and end at this orange point here. It then continues to the edge of the map itself, at which point it disappears. And so what this method has allowed us to do is it's allowed us to just use one location and then predict likely locations where we would find the same layer of rock outcropping on the surface of the Earth. And obviously this is extremely helpful when it comes to producing geologic maps, or more accurately, the initial stages of producing geologic maps, when you are maybe trying to predict likely locations where you will find a layer of rock outcropping. Okay, so what we're going to do now is we're going to stop the video here. So please get up, have a walk around, go and get a glass of water, and then come back for part 3, please.